Hello, welcome to section 3.1, Graphing and Writing Inequalities. Today's target is I can graph and write inequalities. Now, when we talk about inequalities, they're different than equations because an inequality means not equal. Okay, so we'll have to think about that when we talk about the symbols we'll learn here in a few minutes or review. The warm-up, let's fill in the appropriate inequality sign. All right, and if I take a look, they are listed there. Maybe you can remember what they mean. But if I look at number 1, I have -3 and -5. If you guys recall, we always have the alligator eating the bigger number. So I'll say -3 is greater than -5. Go ahead, try number 2. -1 is less than 0. And and number 3, if I look at 0.25 or 0.30, which one's bigger? 0.30. Okay, so 0.25 is less than 0.30. So let's think about how do solutions of inequalities differ from a solution of an equation. So we will see where we get some solutions to inequalities here in the future, but when we have a solution for an equation, we have that x is equal to some number. Let's say it's 5. And 5 would be the only value we could plug into whatever equation in order to make it a true statement. Okay, so solutions of an equation, there's typically one solution. And so we'll talk about solutions of an inequality here soon, but think about solutions of an equation have one solution. Solutions of an equality may have many. Let's look at our symbols. All right, we're going to read this first one as greater than. And an example we could write is 10 is greater than 9. Second one, whoops, let's cross this out and write less than. And we can fill in two numbers that make sense. So how about 10 is less than 20? Now we have less than or equal to. And we could have 5 is less than or equal to 10. That's a true statement. 5 is less than. Okay, so less than or equal to. Then, of course, this one would be greater than or equal to. Okay, and we could have the 10 is greater than or equal to 8. Again, that would be a true statement. All right, let's go ahead and take a look about solutions. Solutions to inequalities are any value that make the inequality true. Okay, so solutions make the inequality true. So let's look here. Describe the solutions to 2 times p is greater than 8 in words. So the solutions will be any value for p, and I put that in quotes because that means any value for that variable p that will make this statement true. Okay? So any value for p that will make the statement true. All right, so we're still working with inequalities. All right, what about when I go to graph on a number line? All right, so if I see the less than symbol or the greater than symbol, when I graph it on a number line, I am using an open point. Okay, an open dot or an open point. when I graph less than or equal to or greater than or equal to, I use a closed point. So I use a closed point, and we'll see some examples here shortly. Okay? So ways to remember. If it's equal to, meaning it has, let me highlight this, it has an equal symbol underneath, then fill in the point. If it's, or if there's, let's do this, if there is no equal symbol or equal sign, open point. All right, so all of this, hopefully the inequality symbols are review, but in terms of graphing them with open points and closed points, we have to keep those in mind when we go to graph them on the next page. All right, make sure you have all this, and then let's go ahead to the next page where we graph each inequality on the number line. Now notice for 1, 2, and 3, there are no numbers on my number line. That's okay. I really care about two numbers. I care about the number that is in your inequality and the number 0. So if I plug the number 0 right here, I also need to plot 5. So I can count by ones, 1, 2, 3, 4, 5, and list 5 right there. It doesn't always have to be exact, distance away. You could easily have written a 5 right here. As long as the 5 is on this side of the 0. 5 does not make sense to be on the left side. Okay? So let's go ahead and keep 5 right there. And let's go ahead and graph. I'm going to read this as x is less than 5. Remember my points. If I have a less than or greater than, it's an open point. So I'll place my open point on the number line right above 5. And I have to think x is less than 5. The question I ask is, well, where are the numbers less than 5? Hopefully you were pointing to the left of it. So what I'll do is I'm going to take my pencil or my pen, and I'm going to scribble down to the left and exaggerate the arrow, because the numbers that are still way down here on the number line that are not shown on the number line on the paper, those values are solutions. Remember, when we talk about solutions, it's any number that makes it true. So let's test 0. Okay, if I see my inequality, let's write it over here. I see x is less than 5. I'll plug 0 is less than 5. Is that true? Absolutely. That's why I'm shading through my number 0. Let's go ahead and look at number 2. I would read this as a is greater than or equal to negative 3. Well, I care about where negative 3 is and where the number 0 is. Please make sure that negative 3 is to the left of 0. When I plot my point, I look at my symbol. It's greater than or equal to. Since it has that equal symbol, I'm going to close my point. That means that that is a solution. That number negative 3 is a solution. Where am I going to shade? Well, a is greater than or equal to negative 3. Where are the numbers greater than or equal to negative 3? They're this way. I can test my point 0. 0 is greater than or equal to negative 3. That's true. And now look at number 3. I have negative 1.5 is less than or equal to y. I want you to star this because we must have the variable first. So now I'm going to rewrite this inequality, but I'm going to rewrite it from right to left. So y, if I read it backwards, y is greater than or equal to negative 1.5. Now I'll worry about graphing this inequality. 0, we can do negative 1.5 right here. Greater than or equal to, close that point. And where are my values that are greater than or equal to negative 1? To the right. Okay. And the reason that these closed points are indeed closed is because that endpoint, that value that that point is at, which for number 2 it's negative 3, it makes it a true statement, the inequality. So let's just look at that. A is greater than or equal to negative 3. Well, if I plug negative 3 in, negative 3 is greater than or equal to negative 3. Is that a true statement? Well, yeah, it's not greater than, but it's equal to, so yes. On the flip side, if I go back up to number 1, if I have x is less than 5, and let's plug in 5, is 5 less than 5? No. That's why it's not a true statement. All right, and that's why the point is open. So we've graphed the inequalities. Let's go ahead and graph some more challenging inequalities. We need to simplify. If I look at number 1, think about order of operations. I should do what's inside the parentheses first. Okay, so D is greater than 4 times, well, 5 minus 8 is negative 3. 4 times negative 3 is negative 12. This is the inequality I'm graphing. D is greater than negative 12. We can go ahead and draw a number line. I'll put 0 and negative 12 on it. Think to yourself what kind of line I should, or what kind of point I should plot. Open or closed. And remember, we look right there. It's open. And where are the values that are greater than negative 12? Oh, they're this way. I can always test 0. Is 0 greater than negative 12? Absolutely. And this is why it should be a true statement. Let's go ahead and look at number 2. I have G is less than the square root of 24 plus 12. All right, so let's go ahead and add 24 plus 12. I have G is less than the square root of 36. In the calculators, or in our minds, think of the square root of 36. What are the two values that multiply together to get to 36? If I take a square root of 36 in the calculator, I get 6. So I'm going to worry about where my 0 is, as well as my 6 on my number line. I have what kind of point at 6? An open one. And again, I read this, G is less than 6. Where are the values that are less than 6 on the number line? To the left. There's my inequality, and it's solved and graphed. All right, so now let's go ahead and write an inequality when we're given a graph. We typically use the value of x because this is representative of the x-axis on a coordinate plane. So I'm going to take a look, and that's a closed point at negative 1. And if I look at the number line, where are the values that are part of my solutions? Anywhere it's shaded are part of my solutions. So these values that I just circled are bigger than negative 1. So therefore, it's greater than, and since we have a closed point, I'm going to say equal to. So x is greater than or equal to negative 1. Let's look at number 2. I have x, and I can see my endpoint is at the number 1. Where are the solutions compared to the number 1? Are they less than or bigger than? Hopefully you said less than. And it's an open point, so it's just simply x is less than 1. Last but not least, I have x, and my endpoint is 0. It's a closed point. Where are my solutions? These numbers down here are less than 0. And it's a closed point, so less than or equal to. So that's writing an inequality when you were given a graph. All right, let's see how this applies to the real world, okay? Route 79 has a speed limit of 55 miles an hour. Write and graph an inequality that describes this situation. If we know anything about speed limits, we should stay under them or at them. So let's use, let's go ahead and define a variable x, and then we can write that as the speed of a car. And let's think about this. If it has a speed limit of 55 miles an hour, we should stay at or under 55. So let's apply that to the inequality symbol. So x, again, the speed of your car, should be less than or equal to 55. So I should have 0 and 55. And I will make a closed point at 55 because I can drive 55 miles an hour. And I can also drive at less than. Now, this brings up a conversation with how safe is it to drive very slow on I-79, or can you drive negative miles an hour? No, but for the sake of us just learning how to apply these inequalities to the real world, we're going to just say it's less than. Notice that I did my graph a little differently. You could draw them this way. You could also go back to doing this. Okay, scribble, scribble, scribble with an arrow. Either way works. All right, so let's take a look at the highways problem. Some highways have a minimum speed limit as well. If the minimum speed limit, meaning the slowest you can go is 40 miles an hour, and the maximum is 55 miles an hour, construct a graph to describe the real world situation. So it's not even asking for an inequality, but it's asking for a graph. So I first off have 0 way down here, and I have a minimum of 40 miles an hour and a maximum of 55, which means I cannot go any lower than 40, but I cannot go any higher than 55, but I can go any of these speeds in between. There's the graph that represents this real life situation. And last but not least, you're a member of the USC crew team. The members of a lightweight crew team can weigh no more than 165 pounds each. Define a variable and write an inequality for the acceptable weights of the team members and then graph. All right, so let's first define a variable. Let's use x. And that x is going to represent, we have to define it and write an inequality for acceptable weights of the team members. So x is the acceptable weights of the team members. See how I just pulled that right from the problem? All right, so let's talk about what is acceptable. They can weigh no more than 165 pounds each. So can they weigh 170? No. They can weigh no more than 165. Can they weigh 165? Yes, which means that x is less than or equal to 165. If I draw my graph, hopefully you'll pick out which type of point to plot. It should be a closed point. And where are the values that are less than 165? Way down here. So again, I hope you can see how you can graph and write inequalities from a graph, as well as apply it to the real world. All right, thanks for watching.